cloud recording set. All right. Oops. All right. So, so looking through the syllabus that's on Canvas, what I would like to do today is kind of briefly go through this plan, and then jump into one small example, which will maybe allow us to, at least until we have the data hub available, still want to use some notebook examples that I've prepared, and also it will give us some tools basically to program Python on the browser, and also kind of understand maybe the representations of MIDI and audio. So so here's the syllabus. I put some slides in the modules, but maybe I will kind of skip right now in the intro and the motivation, which kind of talks in general about why we want to use machine learning for music, and some examples of applications of improvisational algorithms or machine improvisation, composition with music, and we can go back. I would like kind of to try to talk a little bit today about the audio signal processing aspect. So going back to the syllabus, I think we can use some self-learning, and I recommend, or I want to use this book, which I also linked. I think I sent it to you by email. I put it on a drive, but now it's linked to the, it's on Canvas. And also there is this other book, Poly PDF, which is kind of more signal processing, traditional signal processing, that I was going to use, at least suggest this as materials that we can go through, and then you can kind of use more time to learn this on your own, just to maybe catch up on things that we didn't cover in depth. So so let me kind of quickly go through the idea of, let's go through these two books just to show what they are. Okay, so I think I have to open this separately. Okay. So I was thinking about well, the two chapters that I want to go through. Sorry for scrolling quickly. Is 4 and 5. So there's basically the question of music representation, and the two main things that we want to talk about is basically audio, the recorded sound, or symbolic, which will be like written text. So if you think about this text to speech, so you have the text and you have the actual speech which is recorded. So this will be the musical notation. So you can go through the main concepts of what musical notation means, and then talk about the formats and some specific considerations about how to use these formats. What makes music be expressive, because many times the notation is only partially representing things. So, and how you go into encoding and representing music in the symbolic format or the audio format. And then the next chapter, which might be a good introduction to people who didn't take the machine learning classes, is this introduction to neural networks. So I was actually going to kind of read with you, go through these chapters together, because I think it gives a good introduction, and instead of like having slides, we can actually go page by page, kind of read this together quickly, or at least I can kind of explain the basics, and then you can read it on your own outside of class. So this is the basic introduction to neural networks. So it talks about the classical examples of what would you use neural network as, basically function approximation, or something that can do linear regression, and how it's being trained by backpropagation or optimization using gradient descent. So this is kind of really the basic things with what machine learning, at least the traditional one, which is not the one that we are so much focusing on, which is the generative one, but kind of the basics of neural networks are basically something that is used for recognition or retrieval or inference. So in this case, you basically map some data to some label, like in any kind of a object recognition task. So this would be basically a task of learning and mapping between your data and the labels. So it kind of defines machine learning and also talks about unsupervised learning, which comes closer to what we want to talk about. It covers the basic cost functions, because the way machine learning works is basically you define the problem in terms of the neural network approximating your data in some way, or providing some approximate answer to it. And given the data, it gives you some output. And of course, this output is not exactly what you want. So you have some error function there. So these cost functions are usually represented using either least mean square or entropy and cross entropy. So these concepts are important for understanding how you represent your machine learning problem. It's actually an optimization setting. So some people even call this gradient programming. So instead of writing programs with statements and ifs, you define your problem as an architecture, your input data, and a cost function or an error function. And once you defined everything, and all of these frameworks like PyTorch or Keras or TensorFlow give you a set of tools to build the architecture and define your error function and your data. So you load the data, you define your network, and you write an error function, and then you don't do anything else. Kind of the magic is given to the machine, to the optimization algorithm. So of course there is a lot of know-how what optimizers to use, how to initialize them, some tricks in learning. So of course, I mean, the know-how is enormous, but the principle is in some sense, I wouldn't say straightforward, but once you get used to this idea, you understand that all what it does, now it gives you this whole setting to an optimizer, and the optimizer now tries to modify the network until it finds a minimum error or finds something that is a stable point, and this is your solution. So now you have trained your network. So now when you give another data in, you'll get the network to do some calculation, give you an output, and you know that this output was trained in a way that it has some good properties, some minimal error. So about the training, the overfitting, regularization, this is kind of important to understand. And what I find good about this book is that basically in like 30 pages, it gives an overview of machine learning. So speaking about, unsupervised learning, autoencoders, so we'll maybe look into one of the examples of autoencoders in my lectures. But the idea here is that instead of mapping input to output, you map input to itself. And the whole purpose of this experiment is that the network finds some kind of interesting representation of your data in this internal representation, so latent states. So your error is basically the ability of the encoder to reconstruct the data. That's why it's called autoencoder. You basically plug in your data into the network, and then you want the network to reconstruct it. Of course, the most trivial way is just it maps input to output, but then it doesn't have any representation that would be interesting. So you put some constraints on the structure of the network, either by having a bottleneck, so it kind of does some dimension reduction, or you put some regularization constraints. So you actually want the network to be structured in some way that it will extract some data, and from this data it will reconstruct So the autoencoder, it's actually encoder decoder, where the decoder decodes back the original data. And the variational autoencoder is, we mentioned this already today, is one way to do this with kind of a probabilistic modeling. And this becomes a very powerful representation tool. The restricted Boltzmann machines are energy-based models. I don't know if we'll talk about them too much, because I think we can just devote a whole class to these, but we'll go through, I do want to go through all of these pages. Recurrent neural networks, which are ways to represent time, and we mentioned them as well. Convolutional, or CNNs, convolutional neural networks. At least people who did visual work are very familiar with these methods. These are kind of filtering approaches. The convolution, which is a filter operation. So people are familiar with this from images, which are like little filters that kind of go and scan through your image and basically do some sort of an operation on that image, either blurring it or maybe looking for edges. So we have convolution also in audio, and convolution in audio is actually filtering. So we'll talk about this. And then the generative architecture, the generative adversarial networks, which are very, I would say, powerful or promising techniques. A lot of people are kind of very excited about them. Reinforcement learning, it just mentions what it is. I don't plan to go too much into reinforcement learning, but we might want to consider at least some algorithms like reinforce, which are used if you talk about sequences, discrete sequences. We might want to think about so-called learning these policies as part of representation learning. I don't know if we'll have time to go too much into this, but that's another very powerful technique. So this is kind of and combinations of things. So these are the two chapters that I would like to go through in my introduction lectures. And the other one is this poly PDF. And this is really just signal processing using Python. It has a lot of different examples. And I wanted to talk about the idea of filters and transfer functions. So this kind of has to introduce these notions of Fourier transforms that usually in computer science they're less discussed. This is kind of electrical engineering stuff, or for music students, right? We deal with frequencies and decompositions. So one thing that I wanted to kind of talk about and make sure that everybody feels comfortable with these concepts is so-called the representation formula. And the representation formula, I don't know if I can jump there, is the idea that you can, I'm just like giving you like a look forward, is this idea that you can represent a system, sorry, oh, I'm kind of jumping back and forth. You can represent a linear system as this is a convolution, okay? This is a convolution operation, not as a CNN, but just as a standard convolutional signal processing approach, where you have a signal and it goes into something else, which we call a filter or an impulse response. So I want to talk about this, and this is your convolution operation. And actually, a lot of musical signals could be represented as some kind of a source filter model, where you have some input X that goes into filter H, and what you hear is a Y. And people use this to represent sound, like speech source filter models, but also like room acoustics. You have your sound, and this is your reverb. So we want to talk about this is in time. Okay, so we want to kind of illustrate that. But then the basic other notion that is important is, okay, you can represent this in frequency. So we'll talk about frequency or Fourier transforms, but this is kind of a representation formula that I want to cover. And this is the idea that your convolution in time is multiplication in frequency. So this is the usual time domain thing that we showed before. And these are the frequency of the Fourier transforms of X and Fourier transform of H. So convolution in time is multiplication in frequency. And why it's important? Because in a lot of the analysis that we'll do, we'll basically go through Fourier transforms, okay? And we want to understand what this Fourier transform means. And one of the ways to think about this, if let's say X is an impulse, which would be you know, a signal in time which is zeros and suddenly one. In frequency, this will be all the frequencies together. This becomes a unity. So your filter becomes, you can look at your filter either as a convolution in time, as an impulse response, or the frequency response, the H. So you can actually take a Fourier analysis of your filter and know what it does to any signal. And we'll talk about the importance of phases here, and the filtering operations. So we have a notebook that I have. I've had this example before. I think this book also gives you little Python excerpts somewhere. I didn't go through them, but I want to go through the math and show this. So the idea of representing your audio system by taking a Fourier transform of your signal, of your filter, and then knowing that you can either do convolution time or multiplication in frequency domain, but you also have to maintain these phase relations because these are now complex functions. That this is kind of an important point, and I want my plan is to go through these things. So this is kind of the heavy part of what I was going to talk about, which is an overview of representations and of neural networks, and a little bit more the idea of convolution, the representation formula, which is this multiplication frequency versus convolution in time thing that I mentioned, spectrogram inversion and Griffith limb, which is the idea how you reconstruct the signal from the frequency representation without having the phases. And this is important for a lot of vocoders when we do speech to text or singing, but also for possibly other audio related operations. We usually consider just one part of the frequency representation, which is the amplitudes, and we throw away the phase. So I've been throwing a lot of technical concepts here, but this is part of what what I would like kind of to cover as the basics. And so filtering, spectrogram inversion, and the third resource that I would like to use for this seminar is this website, the Music Information Retrieval. Actually, it also I linked to it from also the representation chapter, and let me go quickly there. It's a little bit of a book-like set of Python notebooks, and this is the part we skip, but it has a lot of notebooks that deals with symbolic and audio representations. I mean, I have my own, but this could be also a good resource to go through. And mostly, I wanted to kind of look into some of the classical signal analysis, which means not machine learning based, but just features that you extract by like human engineered features, mostly looking through the spectral or the frequency aspects of the signal, and some more musically designed features like chroma. So this is kind of a nice overview of signal analysis in the classical way, and maybe even more music specific things like detecting onsets. And so I chose only few things out of these two things, the signal analysis and the rhythm and tempo, which I put here. When I say chapter, when I refer to this, I mean just if these are chapters, these are the numbers. So what I was planning to go here is in the audio and feature extraction, basically 1 and 3, just the rhythm, tempo, and beat tracking. And then maybe before that, I also referred to the music representation 1, 2, 3. So I kind of like did a selection of the basic things I wanted to go through. Let me kind of just check it again. In the representation part 1, 2, 3, that was something I kind of looked through and I thought it's good. So yeah, sheet music representation, symbolic representation, and audio representation. Okay, I skipped the tuning systems and stuff like that. But of course, you're welcome to look through all of them. And then I'm planning to go through in the audio feature extraction. I want to go through 6, 7, and 10, which is signal analysis and feature extraction. Yeah, I think 6, the short time Fourier transform, the constant Q transform, and some spectral features. So these are the ones that I was going kind of to go through more specifically, just because I mean I'm going to cover Fourier transform unrelatedly. So 6, 7, and 10 here, and then for the rhythm and tempo 1 and 3. Just what are novelty features and onset detection. But basically, kind of the onset detection is the one I wanted to look at, but it requires to look into novelty functions. So this is there's a lot of reading materials here. Okay, now just going a little further, this from here down, it more becomes like research ideas or things to cover, and I have some notebooks. So at a certain point, we want to focus on generative models. And the generative models are the GANs, the variational autoencoders, and also today there are these incredible results using so-called flow-based models. And in speech, there is the WaveGlow that becomes very, very impressive. So kind of the logic is that, as I said, you take your data. So this is an autoencoder, right? We take the data, we input it, we wanted to reconstruct. Just it's variational because you go through some probability here and not just the mapping. So it becomes mapping into some kind of random function here. This is also a generative model. Z is noise, is random function that generates something, but it's learned through another discriminator. Actually, there's this disconnect, which is very powerful because it allows us to learn things in the discriminator without having really to define that error function. The discriminator becomes the error function. It tells you what's good and what's bad. While in these settings, you need to write your, decide what kind of error function you use. And you have to do some assumptions about the distribution. So, so this is a very powerful method, but it has some difficulties if you want to use this to control or generate from it, because there is no input. This can just generate, but every time it will generate something new. Here you can say, oh, I can input something, and it will now create something in the output. So you can maybe interpolate, maybe you can do style transfer. You can do some other things. Here it's much more difficult unless we do things like peaks to peaks, which means we pair this with some other input, and then the generator can maybe generate something that we want, and not just anything that it knows how to generate. In flow-based, the thing is that here there is actually no bottleneck. These are bottlenecks. You can see that, you know, just graphically, it reduces kind of the data from a lot to smaller representation, from big input vector to small internal kind of set of latent features. Here, the flow-based network actually keeps the same dimension. This Z is small, but it actually is the same size as X. This box is a mapping of your data to some kind of a random noise and inverting it. So maybe because this is all invertible, it's really a very different way to look into machine learning. It's just learning a function that maps noise into what you want, but it allows you, much more detailed and refined control of your output. So I mentioned wave glow here and stuff that we spoke about either singing, or this is from one of the voice cloning papers, but it explains that the reason I want to maybe talk about this for 1 second is just this framework. So what we have some symbolic input. This is from text, but it could be from music or a singing voice. It could be text and musical notes. You have a synthesizer, which actually takes the symbolic data and creates something. So actually the synthesizer is not end-to-end. It usually creates another representation, which is this spectrogram. So we need to understand what spectrogram is, and we mentioned that we're going to talk about this spectral analysis. So it actually takes text or symbolic representation or some instructions or synthesized instructions and creates an intermediate frequency domain representation. And this is then rendered by a vocoder into the waveform. So from this middle representation to the actual audio, there is this whole other box, or this whole other set of knowledge, and things like WaveNet, WaveGlow, Sample RNN, they're all neural vocoders. And the word vocoder that Devansh mentioned is more of a traditional one. So there are separate questions. One is how to go from this spectral representation, which in some sense is reminiscent of musical notation. It's frequencies over time. How do you actually generate audio from this? But here there is this other aspect, how you go from totally symbolic thing into this spectral representation, which actually encodes a lot of performance aspects. So if you think about this as speech, anything that has to do with your vocal expressions, the whole kind of accent, phonetic emotions, style, that usually goes into this part. And specifically for the paper that I took this figure from, you have this idea that you can actually also do this sort of a deep fake. You encode your speaker and you can change the instrument or change the voice that speaks. So I mean, this is, I think, more of the overview of where these things go once we have the basics. And the last thing is, it's a recent chapter that I wrote for a book about music information dynamics, and it kind of represents or talks about this whole field of generative machine learning more from music information dynamics approach, which is slightly different way of looking into this. If time allows, I mean, I'll be happy to go through this chapter. It kind of summarizes a lot of work on machine improvisation, but looking not so much from neural network perspective, but more as an information theory, encoding, decoding aspects. So that's kind of a different way to look into this, but it's I think it's a slightly different perspective. So since we're kind of running a little bit short on time, I want to dive into one more thing, which is using some of the notebooks, okay? And I will use this also as an opportunity to talk about the relation between MIDI and audio, okay? So I'll go here, okay, on the notebooks. So on my GitHub, if you click this link, okay, I have put a lot of notebooks. Some of them I will cover, some are not. I'm not even, I had even problems running this the way I want to show right now, because the way I've set it up is that you can run this on the web. Okay, you can run this now. You can do the same thing. So if you can do this just with me. If you can go on this link and just click it, and you should open the GitHub here. Okay. If anybody has, has any issue, either raise your hand. I think there is a little button that allows you to raise the hand, or jump into.
Shlomo?
Yeah.
Would it be possible for you to just copy the link of GitHub on in the chat, because for some
Oh,
reason
okay.
my canvas is not loading.
Right. Sure.
I can
Okay.
do that. I have it up.
Okay. So
Thanks.
let me see how I can put it on the chat.
I
you put it. Okay, you put it on chat. Okay, thank you. Okay, great. So sorry. So if you go back to this notebook, I'll keep moving forward. But if you lose me, just let me know. Okay. So if you're here, what I'm using right now is a website. I don't know how to call it. The service called Binder. So next thing is, if you can click on Binder, and it will take you to this mybinder.org. And what it does, it now will build an instance with whatever packages and dependencies that I specified. And so now it starts building this runtime environment, so we can actually run this, or you can run this with me on your own machine. Of course, you will be running your own copy, but it will open a Jupyter notebook. It will take a few moments to open a Jupyter notebook in the browser. So while it does that, just kind of to give an idea what it does is that it's a session that once you close it, it will of course die. It's not an ideal way, or actually you cannot develop on this with this tool, but you can run your Python notebooks interactively on the browser, so you don't have to install anything. And in case you use packages that need to be pip installed, or a lot of dependencies, this is being handled right now by the binder. Another way to kind of go through this, let me open another tab. If you want to develop without installing Python on your machine, I mean, another way of doing this is using Colab. I don't know how many of you have tried that. For some reason, you have to be logged in UCSD blocks Colab, but you can also run. So if I have to switch accounts, if I go to my Gmail, or I have a couple of Gmail accounts, so and I open my drive, you can actually, if you do the linking, you can actually go and where's
You are in CST.
yeah, this is the right, yeah. So if I go here, I have a Google Colab. You actually have to connect this app, okay? But if you connect it, then you basically can have notebooks that at first I thought maybe to use this. I copied a lot of notebooks here, but then this way I can run this, but then I have to share the notebooks with you, or you have to copy them because you cannot access, or I mean, it's just an alternative way of doing this. But I mean, this is another way where you can actually start and run your code. So the big difference between using Colab and what I did with Binder is that here it actually installed everything when it opened the binder. I actually had to write a little file there that gives all the requirements. If you do this on Colab, you actually have to pip install. You can write a command in your Python notebook and ask it to pip install every dependencies that you need. Might be a little technical right now, the differences, but this is an alternative tool, and you can explore this a little bit more in depth, and maybe we'll go back to this later because it's also a nice way to develop. So you don't have to deal with your CUDA drivers and maybe not have the right version of TensorFlow on your machine, because here somehow it's very robust. You can open an instance and you just basically click on this, you have your code, and it will not run right now because this one will use Librosa and I didn't pip install Librosa, or maybe this one will actually, because I think it should have Segit's audio, but you can connect it to a runtime, and I think you can even select what kind of runtime you want to use, and it has GPUs. So in your selection, I'm already running this, but you can actually change your runtime and have some GPUs available for your execution. So I'll close this and go back quickly to. Oh,
Shlomo,
sorry. Yeah.
I had a question.
Mm-hmm.
For the Google Collabs, how do you like where do you pip install your packages?
Oh, you write this in. Uh, so let me go back to the drive. Uh, okay, that's actually different. Okay, it's a different Gmail. Okay, so let's say here. Okay, I have this notebook. Oops. Okay, open with Google Colab. So here, you basically, can you
Okay.
see this? Yeah, you
I
just
see.
do exclamation mark and you pip install TensorFlow. Okay, and then pip install OpenL3. So that kind of reminds me, this is something that it's not a project that I defined or offered, but I would like kind of to float this because this is something that I've recently got into. And so there's this initiative. I think I didn't mention, put it here so I would remember, but I forgot about this. There's this project unrelated to music called Kafona. So if nothing, just, and I'm not sure how well it works for on Chrome. I think I had to switch to a different browser to record it. But I'm helping this group of people. I mean, they're pretty much all over the world to collect sounds of coughing from healthy or sick people, where the idea is eventually to create some sort of an audio recognition tool to diagnose people early from their coughing. So apparently there is a difference in the sound of coughing, dry and wet, and also progression through a disease if you have one. So we're going to publish that database pretty soon. There are a couple of parallel activities. This is kind of just a crowdsourcing one. There is another one which is done in hospitals. So if nothing else, spread the word, and you can kind of cough and record some of your stuff. So one of the projects that I was kind of thinking of is I'm kind of trying to run so-called OpenL, the L3. So there are some pre-trained networks which were designed for just sound event detection. They were trained on these pairs of images and videos, and one is VGG, another one is L3, and this is a pre-trained representation, and the idea is kind of just to go, you get an audio, it creates its own embedding. So it's already a pre-trained network. And then the question is, are these embeddings, which are supposed to be very good for general sound recognition, are they useful for representing sound? So instead of looking into spectrograms, these are the embeddings. This is basically 512 dimensional embedding of these 200 seconds of coughing, since it's not running. So this is the spectrogram of the coughing. I don't think if, yeah, I don't, can you hear it? No. I think
No, I think you have to change your audio.
yeah, I have to change the audio settings.
Yeah, you should change your audio.
Yeah, but I think I need to exit the screen sharing for this, right? How do I do this now? I'm lost in. Yeah, I have to. Okay, well, we're kind of running short on time, so unfortunately, yeah. If we can go over like 10 minutes by 9:30, I can try to show this. So let me stop share and share again with sound. Oh, that's new. I did it before. Please restart your audio sharing application social media. I have no idea. I can try this. Okay. Can you still hear me? Hello? Yeah.
Yes.
Okay, so, and now let's see if I do have the sound shared. See if I go here and I play the sound, right? Can you hear this?
This is the recording, okay.
Yeah, this is the recording. So yeah, so that's just an example. Okay, so I'm trying to use this for, hope I'm not confusing everybody. This is two things at the same time. One is running this on Colab, okay? So when you run this in Colab, you have to install every package. So here, pip install TensorFlow, pip install OpenL3, okay? You import them, you import sound file and everything. So this is all the functions. Actually, it still has apparently the memory. I think it resets everything every 12 hours. Unlike the binder that once we close the session, everything dead. This keeps it for, saves it for 12 hours. But you have, first time when you run it, you have to install all the packages. So here it's still alive just because I was playing with this last night. So you run your Python notebook. And again, if people are not familiar with Python notebooks or have, questions, also send me an email. You can put it on, well, if you put it on chat now, I will browse this before we log out, but it will be lost. So it's best if you can send me also any questions if there are things that I skip. But this is mostly showing you a tool, but also I'm kind of like telling you about some project that recently I got into, and I don't know if we'll be able to do something useful and help. But this is one of the ideas, was to use these L3. It's the OpenL3 tool. So I didn't develop anything here, but get these audio embeddings and analyze your sound with these L3 embeddings. So we'll go back in a second to talk about spectrograms, or at least we'll continue with this next week or next meeting. So spectrogram will give you, this is the way it's represented here, this is time. So I kind of, this is transpose, so this is time. And these are the features. So there is a 512 embedding that I did. Specifically, this get audio embedding allows you to specify the embedding size. So this is kind of a representation of short segments of audio. So we have these 200 and something snapshots of audio represented as features. And now this is, it's hard to read, it's hard to understand. We don't know what the features mean. This is the audio recording, right? So this is the audio, right? Very different ones. Okay, I think you got the idea. And this is the spectral representation. So this is time. Now this is in actual seconds, not frames. And this is hertz. And to do this, I'm using Librosa, which is a package that we're going to talk about. And this package is by Dan Ellis from Colombia. It became kind of a, the go-to package for any audio, I wouldn't say speech, but general audio, like musical audio analysis in Python. So this Librosa has this spectral analysis tool. So actually here I extracted MEL spectrogram. So we'll talk about what MEL spectrogram is. It's frequency wrapped in nonlinear way as a MEL scale. So Librosa extracts this feature from this audio and it gives you this matrix. You rescale this and we plot it. So what we see here is time and frequency. So every cough has this kind of a pattern, okay? And the blue one are silences. So then the idea was, okay, instead of looking into these spectrograms, we can look into these embeddings. They're visually much less revealing, but maybe they are more meaningful for classification. So just as an experiment, run some kind of a low dimensional representation with TSNE. Again, something we didn't cover, but this is another very popular tool just to do a dimension reduction to few dimensions. I just took 2 dimensions, and this is what we see. These are kind of like, it kind of splits the cuff into regions, and then maybe, again, we don't have enough data to actually teach a classifier, but definitely there's some kind of a regions maybe. This is of course continuous because people kind of cuff in ways that a lot of frames are similar, but there are categories here of different instruments. So this is an audio classification task where you take the features, and then after having the features, you do some kind of a supervised step, which we still didn't do. This is just an unsupervised step just to look into audio embeddings of these cuff segments, and then basically try to segment them according to regions where there's a big jump in time, because I knew it's subsequent. But I mean, I think that's enough about this notebook. It gives you an idea of what notebooks are and what Colab is. I think we're kind of running short on time, where we're almost done. So instead of doing Colab notebooks, I set up the binder. And what I actually was planning, and this is where we'll continue next week, was now the binder actually is running a Jupyter notebook on a different website, something that, binder, the Jesse's.org that belongs, yeah, it's the binder thing. So if we go now on my deep and shallow folder that, come on, why there is a server error? Did it kill the binder? Okay, I don't want to go and, and repeat the whole thing again, but let's before we I think we have about a minute or something before people have to go. So if I go back here, okay, I go to notebooks, I run the binder, it will start building it again, which is going to be pretty frustrating. But until it builds, I can still browse the files, okay? So if I go on deep and shallow, oh, okay, actually it seems to be running already because it has these functions here. I go on deep and shallow. What I wanted to look at, basically jump immediately into this MIDI and audio lab Python notebook. So if you click on this, so if you had the binder running the way we started this discussion before going into Collab, so I'm back to talking about the binder. Audio MIDI Collab, you can actually run it. You can run it step by step on your own machine. So I'm doing these, execution things. And if you try to do this, the way right now it's set up, it will run into an error. So first of all, what this immediate audio lab does, okay? What I want to talk about next time is these two packages. One is Pretty MIDI, which is something that handles MIDI files, and one is Librosa that I mentioned a second ago, which deals with audio. So the purpose of this little lab, kind of just a startup thing, is to explore the relations between music notation and spectrograms, or how we represent notes, where we basically write, on the piano roll. It's basic. Well, I have to show what the piano roll is for people who are less familiar. But here are some functions that basically take a MIDI file. This one goes piano roll to Pretty MIDI, and the other one goes from some frequency representation CQT to piano roll. I will explain this later. And the idea is, okay, we can now load a sound file. So the way it's set up right now is that the sound file is missing, okay? And it's intentional in the sense that, actually it was not intentional when I first loaded this, but then I thought, well, let's leave it this way because I can show some ways of using this tool. So I'm trying to load a sound file here, and basically tells you that the sound file, I think that's because the sound file is not there, right? If I try to run this, right, that's what it tells you. It crashes, no such file, right? So it doesn't have a sound file. So what do we do in such a case? Well, I mean, actually, it's pretty convenient because we can go back to this Jupyter, okay, and we can upload the file. So if I go here and I look for, where are we? Pretty MIDI. I think I had, okay, if it's not here, sorry, I thought I had the files here. Let me quickly find that sound file. Yeah, so I can take now, actually I'm going to miss two files. I'm going to miss the MIDI file and the WAV file, and I prepare them specially so we can see. One is the MIDI file, which are the notes, another one is the recording of these notes. So if I use them, I can upload them into Binder, and then if I go back to the notebook, yeah, now it actually has the sound file. I can play it. I hope the sound is not too crazy loud. Um, okay, just 3 notes. So what I loaded here is actually the WAV file. And then I also going to load a MIDI file and represent this as a piano roll. So here is the representation of a piano roll. We have these notes represented from the MIDI. And, oh, sorry, no, the piano roll, CQT, this is, sorry. Okay, so I think we're kind of running out of time, so I will go through this again, but just to finish and go all the way down so we can kind of finish the video. Whoever has to go, I apologize. So this is a sound file. We analyze this using librosa into this constant Q transform, which is a different version of spectrogram analysis, or you know, using frequency analysis in different bands. And then we can plot this as if it looks like piano roll, and this is what librosa could extract from the audio. If we keep on running this, let me see where we are. Okay, and then there were actually two questions here. I think I skipped a little plot here of the MIDI piano roll itself. Oh no, sorry. So it didn't. Okay, I didn't use the piano roll representation here. And then the question is, how can we now take this and we can extract and translate this to actual MIDI file? So the purpose of this notebook is to take this now like a spectral representation or constant Q transform representation, and write a little equation, basically rescales this into what would be the signal, the audio time, and write a MIDI file that will basically write this as notes. So we'll start with this next week. I will go slowly through these steps. And the purpose of this is actually to show the duality between musical notes, which are usually represented as, you know, either music notation or as a piano roll. These would be specific notes being played, or the audio analysis, which actually is a waveform, which is then analyzed in frequency, and hopefully, at least for this very kind of synthetic example, you could extract these peaks in frequency and identify them as notes. So this comparison will allow us, this little lab will allow us just kind of to have a hands-on kind of concrete example of, you know, what is the symbolic representation of music, what is the audio representation of music, and how you go through audio representation into frequency representation, and then try to see how they correspond together. So I think that's kind of pretty much an overview, because I didn't really manage to explain in detail, but we'll start with this next week. So right now, let's, my kind of suggestion or a recommendation is you can try to look into this Python notebook and see if you can solve that little task of basically rescaling it and writing back the MIDI file. I can also share with you these two. I'll put these two sample files back in the on the GitHub, so you don't have to look for them. So you won't have this error, but you can still go ahead, and so I'll kind of push this on Git. So look into this, and maybe the chapter from the deep learning book that talks about representations. This is kind of our first topic, and then, you know, thinking about projects. This is basically an ongoing thing. So if you can kind of start defining the projects, or send me some papers that you were looking through that you would like to explore, So we kind of do this in parallel. Now I'll do these classes, but we kind of continue that research. And for the newcomers, basically Rebecca and Divyang, will maybe can think about if you're interested in that visual. Although I think Divyang, you said you're interested in query-based, so we have people who are doing the query-based, like I mentioned Stella already, who is not here, and maybe a couple others. So maybe we'll discuss this again next week, and hopefully everybody will be present. So any questions, requests? Okay.
Thank you.
All right. I hope it wasn't too overwhelming. Feel free always kind of to email me or any feedback or questions about what we did today.
So like next week, when's the time for us to meeting, or we just discuss later?
That's a good question, because I didn't set it up. Did we say that Monday noon is okay?
I think Monday morning is okay, but like 10 to, I don't know, like Monday morning.
No, I was thinking 12:30 to. Okay, let me check because I think there is a section of one of the classes that I'm teaching which is Monday morning. I don't have to be there, but I'm supposed kind of to check in on that. So I was thinking from 12:30 to 2 basically as an option. But I'll put a couple more options, and let's try even today later on to decide when we meet next week, and then just get it resolved, because it takes more energy than anything else, and just to find a good time for everyone. So Devansh, you said you might suggest some 5:30 to 7 meetings, and if that's simple and everybody can do this, maybe we can do this as well. So check that Excel sheet later today, and I will either announce another ad hoc meeting before we set up everything, and maybe that could be on Monday before 2 o'clock, something like 12:30 to 2. If everybody here is still okay with this, and if not, we'll get some other evening time. Okay.
Okay.
All right. Well, so thank you, everyone.
Thank you.
Okay.
Yeah, thank you.
Bye bye.